Hello, welcome to the next video in my sub-series on fixed income, where I happen to be following the sequence assigned to FRM candidates as we find it in the author Bruce Tuckman. That means I'm currently in chapter 4, and here I'm illustrating the idea of effective duration. In my previous video, we looked at DV01, also called the price value of a basis point. That's a very popular and important measure of sensitivity for bonds and fixed income. That one we needed, especially when we want to hedge. When we talk about the risk sensitivity measure, easily the most popular is duration, and it seems like there's a lot of flavors of duration. I'm going to start with effective duration because effective duration is the one that is robust, that allows us to approximate the modified duration. And so in a way, there's not really a huge difference between effective duration and modified duration. It's really more the approach. In either case, we're trying to get here at duration, which is a function of the dollar duration, which itself is the slope of a tangent line, or if we can't get it analytically, we're going to get the slope of the very nearby secant line by retrieving the price at 2 points on the price yield curve, and that's the approach that is called effective duration. So first I'm going to show you how we extract the effective duration from what we call a simple primitive example, that is a 30-year zero coupon bond, because this is just going to be an easy case to understand what we're doing with effective duration and why it's really about the slope of a line. And then after we understand it in a real simple case, I'll just show you Tuckman's exhibit. And at that point, then it should become very easy to understand how he's getting the effective duration from the data points that he's observing from the market. Along the way, I'm going to write out one version of the effective duration that we see often, but by approaching it this way, by understanding it this way, we're going to be able to handle if we see different versions of the effective duration, which we sometimes do. They're not really different. They're all retrieving the slope of this secant line as an approximation to the slope of the tangent line. That's getting us the dollar duration, and then really dividing by the price to convert that dollar into an amount that we can use as a percentage. Before I show you Bruce Tuckman's textbook example of effective duration, I thought it'd be easier to understand it visually with a simpler example. The simplest one I can think of uses what's called a primitive in fixed income. My primitive is a zero coupon bond. It has 30-year maturity, and then with a face value of 100, I'm plotting here the familiar price yield curve that we know to be nonlinear. This plots on the y-axis the price of the bond as a function of its yield on the x-axis. My yield further is with continuous compounding. The reason I do that is that's a special case. When the yield is continuously compounded, the duration of a zero coupon bond equals exactly its maturity. So this zero coupon bond with 30-year maturity has both a modified and a Macaulay duration exactly of 30 years. So that's very convenient. My price yield plot is nonlinear, and in the fixed income class, we say that has positive convexity here. You can see, for example, at a yield of 6%, the price is less than $20. So now, if I go to understand the effective duration, what I'm going to do is I'm going to pick 2 points on this price yield curve and draw a straight line, and the slope of that line is going to be used to approximate the slope of the nearby tangent line. This is what an effective duration does. Probably you're familiar with a tangent. If I had to pick a point right here, these points are at 3% and 4%. About in the middle would be 3.5%. If I pick a point on this line of tangency, as you probably know, tangency by definition means that that line would intersect only at one point to the price yield curve. Well, the slope of that line would be the dollar duration. Now, the effective duration shocks the yield and prices the bond at 2 points, just like I've done here. So I've priced it, I would start at 3.5% and then go minus 50 basis points, plus 50 basis points. So I'm effectively pricing the bond at 2 points on this price yield curve. And then that straight line is very close, you can see, to the tangent line. Not exactly, because it's going to fall inside here, actually defining its positive convexity. But this line is called a secant line. That secant line very closely approximates the tangent line. So effective duration is just using the slope of the nearby secant line to approximate the slope of the tangent line, which is the bond's dollar duration. And so we use it when the analytical duration is difficult or impossible to access, and we have this method here, which is more of a simulation-based method, just retrieving 2 points, getting the slope, that's the dollar duration, and then using that to get the duration. And that's all effective duration means. Effective duration in this way is an approximation to modified duration, which is a function of that more exact slope of the tangent line. So in my example here, now to put numbers on that, you can see, let's say I want the modified duration at 3.5%. And so I could go down to 3%, down 50 basis points to 3%, up 50 basis points, or I'll actually draw that right here. I want the modified duration at 3.5%, so I go down 50 basis points and up 50 basis points, down to 3%, up to 4%. I retrieve the prices of the bond, and that's right here. So at 3%, my bond has a price of $40.66. At 4%, my bond has a price of $30.12. So those are the 2 points. Now, what's the slope of that line? Well, I always think of rise over run that I learned in pre-calculus, I think, right? So where we have in the numerator, what's the rise or the change in my numerator is going to be 30.12 minus 40.66, right? So basically we lose a little bit over $10 as we increase the yield, and my denominator is the 4% minus the 3%. So that's the thing about computing the slope. We just want to be consistent in rise over run, right? For a 1 basis point here's my 1 basis point shift in the yield and in the denominator, and then what's the associated change in the numerator with the price, right? So this turns out to be, let's see, in the numerator, negative $10.54, and then the denominator, I have 0.01, and so this ends up being, it looks like negative 1,054, a rather large number at first glance. Now, that's the slope of this secant line that's approximating the point of tangency at 3.5%. And so here's the point that new learners oftentimes miss, and even experienced professionals sometimes get confused. That slope that we've just computed is not the duration. You can see in my formula, it's right here. That's my first derivative, change in price with an associated change in yield. And that's what's called the dollar duration. It has a large number here because it's the change in price that would be associated with a 1 unit change in my yield. Well, what's 1 unit? 1 unit is 100%. It's actually much bigger than this whole scale. So as a linear approximation, that's saying if the yield increases by 100%, this line is estimating a drop of $1,000 on the price. So mathematically correct for the line, but the units don't make any sense at all. But again, the point there is that that's the slope of the line, that's the dollar duration, and then per our formula, we need to divide that by the price to get the duration, or in this case, the effective duration, which is approximating the modified duration. So I'll just clean that up a little bit, and we know that our first derivative, change in price with respect to change in yield, is negative 1,054. And then we're going to multiply that by negative 1 divided by the price. And that's the price at 3.5%, which is about $35. So I'll just write that in above in place of it. And so this is going to end up being pretty much pretty close to 30 years, which is our effective duration, right? All we did, we took that slope of the line, dollar duration, multiplied it by negative 1 divided by the price at 3.5%, and that converts us from dollar to percentage, really, and gives us the effective duration of almost very close to 30 years, which is going to be the approximation to the modified duration, which would be the exact solution at 3.5% per an analytical solution. My example is simple because we didn't need to do an effective duration here. In such a simple case, we have access to the analytical modified duration, which is exactly 30 years, given my continuously compounded yield. But we're doing by pricing 2 different points, computing the slope of that secant line, gets us the dollar duration, then dividing that by P and negating it, so the negative converts to a positive. We've computed the effective duration of almost exactly 30 years as an approximation to the modified duration, which is exactly 30 years. We can see just a couple of things. First, we maybe start to understand by convention why there's a negation in this calculation for the modified or effective duration. The slope of the tangent or the secant line, which approximates it, is here obviously negative. So our dollar duration, strictly speaking, is going to be negative. And then the negative then converts this into a positive, such that by convention, right, a positive duration is what we expect with the vanilla bond, such that an increase in yield is associated with a decrease in the price of the bond, right? You can see mathematically that's a negative relationship, but such that this derivative here is negative, but the negative here translate that into our normal expectation for the definition of a duration. And then secondly, the reason that I teach it this way is that our understanding is robust to the slightly different versions of effective duration that we sometimes encounter, right? So typically then we'll see effective duration defined in a manner like this, right? We'll have negative 1 times the price. Negative 1 divided by the price, right? So that's going to be the division of the price here. And then we know what's coming here is going to be the slope of the line, the first partial derivative, or an approximation of it. And so what we get in the denominator here usually is the price with if we shock the yield, minus the price, or the price here is if we shock the yield up, minus the price if we shock the yield down, divided by 2 multiplied by the yield shock. And then what candidates in the FRM ask me about every year, I swear to you, every year it's a common question. They'll see different versions of this with or without the 2. And they don't need to worry about that if they have an understanding as to what this formula is doing and the fact that this right here is just computing a slope. In my example, right, we're estimating, my example here, I'm implicitly estimating the modified duration at 3.5%, meaning I'm getting the effective duration at 3.5% by starting at 3.5%, I'm shocking down 50 basis points and up 50 basis points, right? So my yield shock is the price at plus 50 basis points, that's right, $30, minus the price if I shock down the yield of 50 basis points to 3%, that's my 40. And the key idea is consistency here in computing the slope. So if my yield shock is 50 basis points in both directions, that's a total distance in yield of 100 basis points or 1%. So in this version of the formula, it's 2 times 50 basis points so that we have 100 basis points or 1% because that's the yield change that's informing the price difference, right? And so that's why we see that. Knowing that's consistency, we can handle the other version of this effective duration. And again, this formula here betrays the fact this is an effective duration because I go back to simulation versus analytics. It's retrieving two different prices, inferring the slope, and then getting the effective duration that way directly by retrieving prices. And in that way, geometrically, we're retrieving the slope of a secant line that approximates the slope of the tangent line. It's the slope of the tangent line that gives us the exact dollar duration before we divide by P and negate to convert it into the duration. And for this reason, the effective duration isn't really different from the modified duration. Those are both the key measures of interest rate sensitivity that we are interested in, single factor measures of interest rate sensitivity. It's just that if this curve were not very vanilla, if, for example, it bended back here and had an embedded call like mortgage-backed securities do, it wouldn't be very amenable here to an analytical solution. We'd have to use the effective duration, as we might have to if it got a portfolio and it got complex. So we just are resorting to the robust simulation-based approach, so to speak, with the effective duration to approximate the modified duration. Okay, so armed with that understanding, I assume we're really ready to handle Bruce Tuckman's example. And Bruce Tuckman's example is, well, he's not using vanilla bonds, much less the primitive zero coupon bonds. He's actually got a futures contract where the bond is the underlying and an option on a bond. So he's got two different derivatives where bonds are the underlying. And so we're already in a situation where the analytical duration is not going to be easy, if even possible, to access, but we can get duration with effective duration, and all we need are a couple points on that price yield curve. And in fact, so that's why in my replication of the table, I highlighted the assumptions in yellow, because we're given these, so to speak, or we observe these in the market, right? We can observe some volatility in some prices, construct the price yield curve ourselves, and then retrieve the effective duration. And here the interest rate is changed from a yield to a par rate. That's a different interest rate. No matter for us. We can actually compute duration based on different interest rate factors. But the key idea here is that as the rate goes up, we've got different prices to observe, and we know what to do with that, right? Right, I'll just go back and take the calculation out, and this does match his exhibit, by the way. And so the first thing I do is I'm going to get the slope, and we know now that it's going to be the slope of the secant line approximating the slope of the tangent line, and I just want to make sure that I'm consistent. I'm going to go and get the price at the higher interest rate and subtract the price at the lower interest rate. That's my numerator. And so that means I need to grab the difference between the same corresponding interest rates. I forgot my open parens minus here. And so I've been consistent, you can see, and you really do understand if you figured out that I actually could have done there's three different combinations that are possible here. I just picked the two endpoints here, but I could have computed effective duration between the middle row and the bottom row, or between the top row and the middle row, and I would expect them to be very close, but I would not expect them to be exactly the same. Now, if I hit enter there, what am I getting? I'm getting the dollar duration, negative because that slope is negative. 744 looks like a very large number, but you're really doing fantastic if you followed me when I said that is the slope of that line, meaning that if we just mathematically honored that line for a 1 unit change in the interest rate, which would actually be 100%, this is implying a drop of $744. It's not to reasonable scale. And so we're going to take that dollar amount and convert it into a percentage by effectively dividing by the price here right in the middle. And we get the 6.217, which we can now say that's an effective duration by definition of the operation that we just did. And further, we can say that's 6.217 years. And we would interpret that just like we interpret a modified duration, which is to say that for every 1% change in yield, we expect approximately a 6.217% change in the price, right? Percentage change in the price. Or generally, if the yield changes by X basis points, maybe I'll say, let's see, change in yield by X basis points, this implies a 6.217 multiplied by X percentage change in the price of the instrument. And then over here in his formula, he also has the similar calculation, or the same calculation effectively for the duration on the option. And initially this looks large, but this is 201 years. And we just have to notice that this is an option. So as befits, it's a highly leveraged instrument. It has an abnormally high duration. We know just by looking at the high duration that it's not a vanilla bond. So that's the effective duration as illustrated by Tuckman. I hope that's helpful. If it is helpful, subscribe to the channel and you'll be notified because I have more videos on duration coming soon as part of this series while I'm following Tuckman. Thank you.